Okay, folks, continuing with section 11.8 vectors, we're done with page 1. We're done with page 2. We're done with page 3. And we're done with page 4. Time to move on to page 5. Page 5, we're going to be applying, for 2 more example problems, we're going to be applying the procedure that was on page 4 for vector applications and navigation problems. So let's go ahead and take a look at what we got here. In question 7, we have an airplane that is trying to fly to a target that is 750 kilometers away at a bearing of south 49 degrees east. At altitude, the wind speed is 90 kilometers per hour from the southwest. What speed and direction measured as a bearing should the pilot fly to reach the intended target in 72 minutes? Okay, so let's take a look first at the wind, because that one's easy to identify. The wind speed is 90 kilometers per hour, and that's from the southwest. If wind is from the southwest, that means that it is blowing towards the northeast. And it is at exactly an angle of 45 degrees here. So again, if the wind, if we consider southwest, wind out of the southwest is blowing towards the northeast. And the magnitude of that vector is 90 kilometers per hour. So we can pretty easily get the wind vector as 90 times the cosine of 45 degrees and 90 times the sine of 45 degrees. And that gives us a component form of 63.640, comma 63.640. And those are in kilometers per hour. So our wind vector is 63.640 in both directions, kilometers per hour. So the next thing that we're going to try and figure out in this problem is we're given some information about where the airplane is trying to fly, and we have to figure out, is that going to help us with the vector v or the true vector t? Well, the key to this problem is right here. The airplane is trying to fly to a target that is 750 kilometers away at a bearing of south 49 east. So that tells us information about the true vector. And the reason why we know that is because it tells us, the problem says, hey, that's where we're trying to get to. So forget about what the wind is doing. This is where you have to get to. And so that's going to be our true vector. And we're told some information about the distance, 750 kilometers, and how long, 72 minutes. So the 750 kilometers and the 72 minutes are going to help us find out the magnitude of the true vector, or the speed that the airplane that the true vector needs to achieve. So that's going to be 750 kilometers divided by 72 minutes. Well, I don't know about you, but I don't want to use a problem in kilometers per minute, so I'd rather do 750 kilometers per 1.2 hours, because 72 minutes is 12 minutes more than an hour, and 12 minutes is 0.2 hours. So when I go ahead and do that division, I get a speed of 625 kilometers per hour. So that's going to be the magnitude of my true vector. Now we have to figure out what the angle is. So we're trying to fly to a target that is at a bearing of south 49 east. So if we go south and then 49 degrees east, that is the target that we need to hit. So this is our 49 degrees right here. I wrote 45. Clearly that's wrong. 49 degrees. So the bearing is south 49 east. Remember, this is south and this is east. So this little angle right up here, that's 41 degrees. And I'm actually going to use that when I try and figure out what the component form is of the vector t. The component form of t is going to be the magnitude, 625, times the cosine of negative 41 degrees. I'm going to go ahead and use the angle measured from standard position, but negative. The signs between cosine and sine will work out to give us the right component form. 625 times the sine of negative 41 degrees. And after you crunch those numbers on your calculator, you'll get the following. The true vector has to be 471.693 in the horizontal direction and negative 410.037 in the vertical direction. So I'm going to go ahead and fill in the true vector in my template up top here. Horizontal component needs to be 471.693. Vertical component negative 410.037. Okay, so let's take stock of where we're at. These two pieces of information in the problem were given. So what we're asked to find is v, the other vector, and that's our adjusted vector that the pilot will actually have to fly at that vector to get to his intended target when adjusting for the wind. So we can easily figure out the different components of v by doing the horizontal component of t minus the horizontal component of w, and that gives us v's horizontal component as 408.053. We can do the same thing for the vertical component of v, negative 410.037 minus 63.640 gives me negative 473.677. So remember, this vector v is the velocity of our plane that the pilot needs to fly, so that after he adjusts for the wind, he actually reaches his intended target in the intended time. And this is actually a calculation that airlines use to get to their intended target. Now, they don't do it by hand like we're doing. They probably use a sophisticated computer algorithm and GPS, etc. But back in the day, this is how they did it. Okay, so what do we got to do now? What speed and direction measured as a bearing should the pilot fly to reach the intended target in 72 minutes? Well, let's go ahead and sketch our vector v up here in our little template just so we know what we should be looking for. So we're going to have a horizontal component of 408. We have a vertical component of negative 473. So that's going to give us a vector down here in quadrant 4. Let's figure out what the magnitude of that vector is. The magnitude of vector v will be equal to the square root of 408.053 squared plus negative 473.677 squared. Folks, make sure when you put this into your calculator, you recognize that even though this number is negative right here, when we square it, it becomes positive. That's a surefire check on your answer. If you get something, if you ever get a negative value under the square root for an application problem, you ought to check your work. Okay, so when I go ahead and crank the numbers here, I'm going to get a speed of about 625.2 kilometers per hour. And you'll notice 625.2 is really close to what our true vector was of 625 kilometers per hour. So in terms of speed, we don't have to fly that much faster than our actual true velocity vector. And if you take a look at why do we actually have to fly faster? Well, the wind is pushing against us. If we're trying to get this direction and the wind is pushing this direction, that means we have to fly faster in this direction to reach our intended target. Now, the magnitude of the wind, 90 kilometers per hour, is so much smaller than our 625 kilometers per hour, that we don't have to adjust that much. But we do have to adjust the angle. So let's take a look at that angle. I'm going to go ahead and call this angle right here theta. And then I'm going to call this angle down here B for our bearing angle. Theta we can get by using inverse trig. Theta is going to be the inverse tangent of negative 473.677 divided by 408.053. And we know that's going to give us a negative angle in quadrant 4, and the output from our calculator there is negative 49.3 degrees. But we need to turn that into a bearing. So in order to turn that into a bearing, I'm going to add that negative angle to 90 degrees in order to get this bearing B right here. And that bearing will be south, whatever B is, east. And when I do 90 minus 49.3, I get 40.7. So that bearing will be south, heads up, south. Okay, a little technical difficulties. I'm going to try not to get frustrated. Let's see if we can get this to work. Okay, right now all of you should be laughing because Mr. Vass can't get the machine to work. South, there we go. 40.7 degrees east. So there's our final answer. That's how the pilot needs to adjust his course. He needs to fly 625.2 kilometers per hour at a bearing of south 40.7 degrees east in order to reach his intended target on time. All right, folks, now we got one more problem here. We're going to look at problem number 8. The SS Bigfoot leaves Yeti Bay on a course of north 44 degrees west at a speed of 9 miles per hour. After traveling 90 minutes, Sasquatch determines he is 24 miles from the bay and his bearing back to the bay is south 13 degrees east. What is the speed and direction of the ocean current that caused this to happen? Round speed to the nearest tenth of a mile per hour and express the direction as an angle measured in standard position round to the nearest tenth of a degree. Okay, so that's all the nuts and bolts of this problem. But this problem's pretty tricky. I'm not going to lie. I believe that some of you will struggle with this. Hopefully I can make that struggle minimum. So what are we given here? Well, we are given the actual the actual vector v, because we're told that the SS Bigfoot leaves Yeti Bay on a course of north 44 degrees west at a speed of 9 miles per hour. Okay, so we know we can go ahead and sketch that vector v. North 44 degrees west at 9 miles per hour. So the magnitude of that vector is 9. This angle between north and west is 40. North in the vector is 44 degrees. But this angle right here is going to be 90 plus 44, or 134 degrees. And that's the angle we need to actually determine the component form of vector W. Vector W will be equal to 9 times the cosine of 134, 9 times the sine of 134, for a total of negative 6.252, comma 6.474. And that's our vector V. 6.252 and 6.474. Folks, this is a new one to me. I have no idea why those large red dots are appearing. That's kind of interesting. I wish it would stop, but you're just going to have to bear with me. Okay, so there's vector V. Does that make sense to us? Yeah, we have a negative horizontal component and a positive vertical component. We end up in quadrant number 2. Okay, so what next? After traveling for 90 minutes, Sasquatch determines he is 24 miles from the bay, and his bearing back to the bay is south 13 degrees east. So this is information about the true vector because it says, hey, he determines this is where he actually is at. So in order to look back to the bay at south 13 degrees east, we're going to say that this is the bay and this is where the boat ended up. So in order to look south 13 east, I'm going to kind of sketch in where that angle occurs. Okay, so to look back to the bay, he looks back to the bay at south 13 east. So that 13 degrees is right there. Okay? And notice how I drew the vector though. So he stops when after he goes for, what did it say, 90 minutes? 90 minutes, yeah, so he travels for 90 minutes. After 90 minutes, he looks back to the bay at south 13 east. That means to get to that point, he had to travel at north 13 west. Hold on a second, Mr. Vass. How on earth do you know that that angle right there is 13 degrees? Well, I know that because I have a pair of alternate interior angles. 13, transversal, and 13. Remember, with an alternate interior pair, with parallel lines, alternate interior angles are congruent. So I've got a 13 degree angle here that is a bearing of north 13 degrees west. If I want to find out that total angle in standard position, I have to add 90 to that. And I'll need that in just a second, so I'm going to go ahead and write that in my picture here. That's 103 degrees. 103 degrees is the angle measured in standard position. Now let's figure out the magnitude of the true vector. So when Sasquatch looks back to where he started, he says, okay, I'm 24 miles from the bay, and that was after traveling for 90 minutes. So what speed did it take for me to get there? All right, well, I've got 24 miles in 90 minutes. I don't know about you, but I don't want to work in miles per minute. I'd rather work in miles per hour. So that's 24 miles in 1.5 hours, which gives me 16 miles per hour. 16 miles per hour is the magnitude of that vector t. Well, I know its magnitude, I know its direction, so now I can figure out what the component form of t is. The component form of t will be 16 times the cosine of 103 degrees, and then 16 times the sine of 103 degrees. When you crank that out in your calculator, you're going to get negative 3.599, comma, 15.590. At this point, folks, I'm ignoring the ginormous decimal points. I have no idea why that's happening. Very frustrating. Hopefully you can ignore that too. Well, you shouldn't ignore that. Whoa, that's not what I meant to do. You deserve better, folks. You deserve better than this obscenely large decimal point. So we're going to fix that for you. Okay, so that's the vector t. I'm going to go ahead and fill that in the template. Negative 3.599 in the horizontal direction and 15.590. What's important to recognize at this time is that these are velocity vectors and these are in miles per hour because that's the units we're working for in this problem. Okay, so what do we have? Well, we have that this was given. That is the bearing, the velocity vector that Sasquatch took when he left Yeti Bay, and this is also given. That's the true velocity vector that would get him to his location after 90 minutes. So what do we have to find? Well, what's left? We have to find the water current that changed this vector into this one. And I can figure out each of these components by doing some simple subtraction. Negative 3.599 minus negative 6.252 gives me 2.653. And 15.590 minus 6.474 gives me 9.116. Okay, folks, we're almost done. Let's just really quickly sketch this out. We're going to have in our little template here for the water current, it's going to have a horizontal component of 2.6, a vertical component of positive 9.1. That vector is going to look like this. And that's the angle right there. So I believe the last thing we're asked to do here is, what is the speed and direction of motion current that caused this to happen? Round everything to the nearest tenth and express the direction as an angle measured in standard position. So now we have to find the magnitude of W and the angle for W. And let's go ahead and do that now. The magnitude of W to the nearest tenth of a mile per hour will be 9.5 miles per hour. That sounds like pretty fast water to me. And then the angle, well, we got lucky here because this vector is in quadrant 1, so I can simply do the inverse tangent of the y component divided by the x component. And when I round that to the nearest tenth of a degree, I get 73.8 degrees. And that's it, folks. So for some vector navigation problems, we have one more page to go in the notes. And folks, I'm going to be honest with you, those last page, those are bonus problems. So at this point, if you're running out of steam with the videos, you might give WebAssign a try and see how much you can get through on your own without looking at those last couple example problems. Good luck to you.